Hello everyone and welcome back. Today we're going to continue our exploration of linear algebra and talk about two very important concepts, the idea of independence and the idea of spans of vectors. So first off, let us define a notation that you're going to be seeing a lot of in the next few videos of the series, in particular this symbol here. So that's going to be a script letter r to the power of n. So Rn is going to be, it's going to have a more complex definition later, but for now let us just define it as the set of all vectors that have n rows and one column, such that the elements of that particular vector are from the set of real numbers. So each of the elements, x1, x2 down to xn, are all real numbers, so no imaginary numbers or other types of numbers allowed in this particular set. So just a couple examples of things that live in the set Rn. For example, example 1, consider the vector 3, 2, minus 1. So is this an element of Rn? So each of the elements are from the set of real numbers. So in particular, this vector lives in the set R3. If we look at another example, for example 3, 2, this has also real numbers, so that's going to belong to R2. And if we have the vectors, for example 3, 2, 0, that has 3 entries, so that's going to belong to R3. And let's look at another example, example 4. So suppose we have 3, 2, and I, where I is equal to the square root of -1. This, although it does have 3 entries, it does not belong to R3. That would belong to, say, C3 or some other type of set of vectors. For clarification purposes, there is a difference between R and R1. So R is going to be a set of numbers. So a set of numbers like 5, -3, 2, 1.2, something like that. And this is the set of vectors that only have one element. For example, this would be the set containing, for example, 3, and this is the set containing the vector that only has one row and one column. Now, although these two sets do have similar structure, they are consisting of different objects. So make sure not to get confused between the notations of what we're actually using here. So now let us define the next very important concept that we're going to be working with when we talk about independence and spans of vectors. So what we're going to first off let is two vectors, x and y, and let us assume they both belong to the same exact set, let's call it Rn. Okay, so n rows, one column, and let us also choose C1 and C2 to belong to the set of real numbers. So x and y are vectors, C1, C2 are numbers. Then this expression C1 x1 plus C2 x2, this expression is called a linear combination of x and y. So first off, let us define what we actually mean by this type of multiplication. So c times x, this is usually what we refer to as scalar multiplication. And if you don't already know what that is, that's the same as, for example, cx1 times cx2 down to cxm. Because x1, x2 down to xn are real numbers, c is a real number, and the multiplication of real numbers, at least in the general sense, is well defined. Right, so that is what a linear combination is. So let's ask a very, sometimes easy to understand question. Can you represent the vector 3, 2 as a linear combination of the vectors 1, 2 and -3, 2. Okay, so can we represent that vector as a linear combination of those other two vectors, right? So in some sense, I'm implying that it's possible that a linear combination doesn't exist. One can also ask, well, is that linear combination unique if it does exist? And maybe some other questions may naturally arise in that conversation. So if it does exist, in a sense, what we're looking for is constants c1 and c2 that let the expression c1 times 1, 2 plus c2 times -3, 2 equal the vector of interest. In particular, that's going to be 3, 2. Right? So that's a matrix equation, one matrix equation with two unknowns. Now we can of course write this in matrix form because we know that this is the same as c1 times 1, or 1c1, and then 2c1, and then plus minus 3c2, 2c2, and that's going to be equal to 3, 2, and that's the same as 1c1 plus 1c1 minus 3c2, and that's going to be 2c1 plus 2c2, and that's going to be equal to 3, 2. So in a sense, we have a systems of equations, right? And keep in mind, both of these are 2 by 1 vectors. So from this, we have the equation, because if these vectors are equal, their elements must also be equal. That's going to give us 1c1 minus 3c2 is equal to 3, and 2c1 plus 2c2 is equal to 2. Right? So we have a systems of 2 equations and 2 unknowns. But keep in mind, we can represent this system as a matrix equation as well. We can write that as 1 minus 3, 2, 2 times the vector c1, c2, and that's going to be equal to 3, 2. It's very important that you understand the difference between these three objects. Okay. Now, of course, this times that does equal that, but they are, in some sense, separate objects, because that is a 2 by 2, that's a 2 by 1, which of course results in this particular 2 by 1 matrix, and that's going to be a 2 by 1 as well. Okay, so does this linear combination exist? In a sense, is also asking the same exact question as, does the solution to this matrix equation exist? So we already know a very easy way to determine if it exists or not. We can just find the determinant of this particular matrix, and let's call that matrix A. So determinant of a 2 by 2 is actually very easy, we know. So that's going to be equal to 1 times 2 minus 2 times minus 3. So it's going to be equal to 2 plus 6, which is equal to 8, which is not equal to 0. Since the determinant is not equal to 0, that means we do have a linear combination existent, and it is also unique. So what is that solution equal to? So we know that we can multiply both sides of this particular equation by the inverse of A, so we can get the solution x is equal to A times the inverse of B. And we already know a fast way of finding the inverses of 2 by 2 matrices. So let's just write that out, what that actually looks like. So that means that C1, C2 is going to be equal to the inverse of the matrix 1 minus 3, 2, 2, inverse times the matrix 3, 2, or the vector 3, 2. So the determinant of that 2 by 2 matrix we already found was equal to 8. So the shortcut for the 2 by 2 inverse is going to be 1 divided by the determinant. Then we're going to flip or switch the diagonal entry, so 1 is going to go to 2 and 2 is going to go to 1, so we're going to have 2, 1, and then we're going to negate the off-diagonal entries, so that's going to be equal to minus 2 and positive 3, and then we're going to be multiplying that by the vector 3, 2. So we should already know how to multiply a matrix by a vector, so that's going to give us 1/8 times 12 minus 4, and then we can distribute the scalar into this particular vector, and we're going to have 3 halves, and then negative 1/2. Therefore, that is my solution to my matrix equation. So let's sort of go back and think about what exactly were we answering in the original question. So that means we were looking for a linear combination of those two vectors. So that means our claim is that 3 halves, the scalar, times the vector 1, 2, plus negative 1/2, the scalar, times the vector minus 3 halves, minus 3 over 2, not over 2, but 2. That does equal 3, 2, and you can check that that statement out, and you should be able to verify that that is indeed true, right? So that's how you can verify if a solution, or moreover a linear combination, does exist between two vectors and another desired vector. From that example, you should be able to generalize that to a broader formula. In particular, if we were to choose any two vectors in the set of two real valued vectors R2, where x is represented as so and y is represented as that, then any other vector, also in R2, can be represented as a linear combination of x and y, provided that the determinant of those two vectors you've chosen, x and y, in column form, is not equal to 0. Now, that's obviously true for R2, and you should be able to prove that. So what if we extend the dimension of the space that we're working in? Instead of R2, what about R3? So let's just write this down. So similarly, if x, y, and z all belong to R3, then all other b in R3 can be represented as a linear combination of x, y, z, provided what is true? So take a guess. So provided that the determinant of the matrix, x in the first column, y in the second column, and z in the third column, so that's going to be a 3 by 3 matrix, is not equal to 0, and you should be able to prove that as well. Generally, if you know mathematical induction, then you might be able to prove this for the Rn case as well. And that's probably the most broadest and most useful of those results, at least that we've discussed so far. So let's see if we can also build another interesting statement as well. So consider the matrix equation given by Ax is equal to 0 with A, an n by n matrix, x belonging to Rn. Let's also assume that A is in all the entries of A are in R as well. And let's also assume that this thing on the right-hand side, 0, also is an element of Rm. So that's not the number 0, that is the vector 0. So some people will put a hat just to sort of distinguish between the number 0 and the vector 0. So that 0 in this case is just the vector containing 0, 0, 0, all the way down to 0, and there's n of them. Okay, so just make sure not to confuse that, right? So matrix, vector, and also vector, not a number. So what theorem do you believe exists via the things we just talked about in this particular equation? Then, if the determinant of that square matrix A is not equal to 0, then we at least know that there exists a unique solution. So there exists a unique solution given by x is equal to A inverse times the 0 vector, okay? So it's not 0 number times the matrix, it's 0 vector times that matrix, right? Because we know if the determinant is non-zero, then the inverse of that square matrix does exist. Now, regardless of what those entries in that inverse matrix are, when you multiply all of them by 0 and add them up, that's still going to give you 0, right? So that means the 0 vector is the unique solution. Generally speaking, some people will also call 0 vector the trivial solution because something times 0 is equal to 0. We know that something, of course, would be equal to 0. But another important question is, are there other vectors that will make it true in the case the determinant of A is actually equal to 0? And that's actually a very important question that we will investigate in depth later on. Now that we understand what a linear combination is, and we've proven that Ax equals 0 has a unique solution, x equals 0, provided the determinant of A is non-zero, now we have the tools necessary to understand the first important idea that we want to talk about today. So what we're going to do is first consider a set of vectors x1, x2 down to xn, each of them belonging to the same set of vectors that have the same exact number of rows, in particular m rows. Now keep in mind, we have n rows, each of them with m columns, and it's not necessarily needed that m be equal to n. M can be less than n, and m can be greater than n. There's some unique relations and theorems we can get from both those cases, but let's assume the general case at this time. And let's also define the matrix A to be equal to the matrix that consists of all of those vectors as columns of that matrix. So this is going to be equal to an m row by n column matrix, which we're going to denote as A. So now let us define what a set of independent vectors is. So then S is a set of independent vectors if Ax equals 0. Keep in mind, A is not necessarily a square matrix here, right? But the same idea can be applied. So if that equation x equals 0 has the only solution, x is equal to 0, keep in mind 0 is a vector, then we say that that set of vectors S is a set of independent vectors. Otherwise, S is a set of dependent vectors. Now, there are other ways of thinking about sets of dependent vectors via the concept of linear combinations. So if S is a set of dependent vectors, then there exists at least two vectors. Let's call them xi and xj in that particular set that can be written as a linear combination of the other. Okay? So if you can write one vector as a linear combination of another vector or a set of other vectors in that particular set, then that is what we call a set of dependent vectors. All right? So if you can write that as a particular linear combination, now it's not just any combination, but that linear combination must be in the form linear combination is equal to 0, where that 0 belongs to the vector space or the set of vectors Rm. So if we look at these particular vectors, xi and xj, and possibly some other vectors, so if there exists some c, which is going to be a set of vectors, say c1, c2, down to say, let's call it c k, where k is the number of vectors that we're sort of analyzing here. And let's assume that this is not equal to the 0 vector, 0, 1, 0, 2, down to 0, k. If there exists this vector c that is not equal to 0, such that c1 x1 plus c2 x2 plus all the way down to ck xk is equal to the 0 vector, then we say that these vectors x1, x2 down to xk is a set of dependent vectors. So that's pretty much what we're going for here. Let's look at a couple examples to sort of see if we understand what these definitions actually say, because sometimes it requires a bit of practice to understand, especially when it becomes a little bit more abstract. Let's consider the set of vectors S, which consists of 3, minus 6, 2, and 5. So is this set a set of independent vectors, or is it a set of dependent vectors? Let's look at the matrix representation if it were to try and find a linear combination to set it equal to 0. So does this matrix equation, 3, 2, minus 6, 5, times c1, c2 is equal to 0, 0, does it have a solution other than 0, 0 for the c's? If we look at this in augmented form, we can write this as 3, 2, minus 6, 5, augmented with 0, 0. So if we find the reduced row echelon form of this particular matrix, and let's call this matrix A, and we look at the reduced row echelon form of that via Gaussian elimination, then we should see that that's going to come out to 1, 0, 0, 1, 0, 0. Right? So notice that the number of rows equals the number of pivots. That means A has full rank. So if A has full rank, then that implies that the set of vectors is independent. And why does that imply that the set of vectors is independent? That means the only solution to this particular equation is c1, c2 is equal to 0. So that's pretty much what we're going for here. Now the reason why I bring up reduced row echelon form in this particular scenario is because the number of vectors that you're analyzing is not necessarily the number of rows that you're working with. Therefore you can't always use inverses to solve your problems, right? So if you can't use inverses, you have to have a general procedure, and reduced row echelon form can sometimes be a very, very big help for you. So let's look at another set of examples where we actually have more vectors than the number of rows of analysis. So let's consider 3, minus 6, minus 2, 4, and 2, 5. So is this set a set of dependent vectors, or is it a set of independent vectors? So if we represent this in augmented form, so A is going to be equal to 3 minus 6 minus 2, 4, 2, and 5, augmented with 0, 0. So if we reduce row echelon form this, we're going to have 1 minus 2 thirds, 0, 0, 0, 1, augmented with 0, 0. So if we analyze this, what do we have? So there is our pivots. So the rank is equal to 2, but we have one free variable located there. So free variable. Okay? In particular, this free variable depends on x1. So it depends on the first variable x1 because remember this x1, x2, and x3. So x2 is dependent on x1. You could also say that x1 depends on x2. We just presented it first in our analysis, but it doesn't really matter in that regard because we're just trying to classify this as a set of dependent or independent vectors. So since we've found that the matrix does not have full rank, in particular the nullity of this matrix is greater than 0, that implies that at least one of these columns is going to be dependent on the other, and therefore this set is a set of dependent vectors, right? And you can see how easy it is if we analyze this from the reduced echelon perspective. The next concept that we're going to talk about is what is known as the span of a set of vectors. So the span of a set of vectors, denoted by span of S, is the set of all vectors that can be represented as linear combinations of the vectors in S. So is the span a vector? Not necessarily. The span is generally a set of vectors. So you have a set of vectors S and another set of vectors, the span of S, which is typically at least the size of the original set. And you can sort of think about that for a moment. Is there a set for which the span and the original set are actually equal to each other? It's actually a very interesting question that you can think about, actually. So let's just do a couple quick examples algebraically to sort of see what we're looking at here. So let's assume we have the set of vectors S, which is defined by the lonely little vector 3 minus 6. So if we want to know the span of that set, that's going to be the set of all vectors in R2, xy, that can be represented as linear combinations of that particular vector, in particular 3 minus 6, where c is a scalar in R. Right? So it's all the multiples of 3 minus 6. So you should be able to see that, for example, if you multiply by 2, 6 minus 12, that's going to belong to the span of S. What other vectors? If we divide by 3, that means 1 minus 2 is going to be there. So 1 minus 2 is going to belong to the span of S. We're going to have 1/2 minus 1. That's going to belong to the span of S. Pretty much any linear combination of this lonely little vector 3 minus 6 is going to belong to the span of S. So if we sort of think about that geometrically, well, where is 3 minus 6? So 3 minus 6 is going to be located somewhere down here. And the span of that particular vector, so if we actually call this vector a name, let's call it u, any scalar multiple of that vector, so that blue vector there, that blue vector there, that blue vector there, the 0 vector also would be in that span there, there, and there. That line, I guess you could say, is going to be the span of S in this particular case. So at least based on that comment, you should be able to know that 0 is always going to be in the span of a particular data set. All you have to do is just choose your scalar constants in your linear combination to all be 0. Now, let's look at another example. I mean, the one vector set is a little trivial, but let's look at 2. Let's look at the set of vectors S, which is equal to 3 minus 6, 2, and 5. So if we just blindly look at this, the span of S is going to be the set of all vectors xy that can be represented as linear combinations of these vectors. So xy, let's call that, for example, u1 and u2, is just going to be equal to c1 u1 and c2 u2 added together. So it's the set of all of them, right? Here, c1 and c2 are scalars. Okay? Now, question. Are these two vectors independent? So remember, if we do the reduced row echelon form of the matrix 3 minus 6, 2, 5, we were able to get the matrix 1, 0, 0, 1, which implies that these two vectors are independent of each other. So if you have two vectors in R2 that are independent of each other, and you were to span all of them, what will you get? So let's think about that geometrically for a moment. So if we have 3, negative 6, that's going to be somewhere down here, and 2, 5 is going to be somewhere down there. So if we look at all the multiples of the blue, that's going to give us that particular line there. And if we scale across that orange, that's going to give us any vector along that line. If we, for example, connect these 2 points, for example, if we add them, for example, if we do u plus v, that's going to give us that vector in green there. V plus u would be the vector in the other direction of that little triangle. And if we were to connect any vectors in these purple lines, for example, in any direction, because we already know we can get any vector along those purple lines, notice that we can technically get any vector in R2 that we wish. And actually, that's one of the interesting properties about spans of independent vectors. Because if x and y are independent and they both belong to R2, that means the span of that entire set is the entire set R2, and that's very, very nice. So if one were to try and compress the answer of a span of a set of vectors, x1, x2, down to xn, where those vectors all belong to, say, Rm, you could always write the span of those vectors as just a sum of the scalars from R times those vectors, and you can write it in a very compactful notation via sigma notation. So let's look at a couple more examples on the spans of data sets, but let's actually increase the dimension from 2 and actually let's look at 3. So example 1. So let us assume we have S, which is equal to the vector 1, 0, 0, 0, 1, 0, and 0, 0, 1. Some people refer to these as the standard vectors or the standard unit vectors of R3 because they're all unit vectors, they're all belonging to R3, and you should be able to see that if we were to compress these into an identity matrix, the reduced echelon form of the identity would of course be equal to the identity, forcing these vectors to be independent. So if we were to span all of them, and since there are 3 independent vectors in R3, then you should be able to verify that the span of those 3 independent vectors is the entire set R3. So regardless of the vectors you have in R3, you can always represent them as linear combinations of these particular 3. Now let's look at a subset of these vectors. So let's look at example 2, the set of vectors consisting of 3, 2, 1, negative 1, 2. So if we look at the reduced echelon form of this set of vectors, you should be able to see that that's going to be equal to 1, 0, 0, and 0, 1, 0. So notice that the rank is equal to the number of columns. That means that we have a full rank matrix. That means these 2 vectors are, again, independent. So what is the span of these vectors? Is it all of R3? The answer is no. We're actually going to be missing a dimension. So the dimension of the span is the number of independent vectors inside of that set. So one could say that the dimension of the span of a set of vectors is equal to the number of independent vectors in S, which one can also say is the rank of the reduced echelon form, well, not necessarily reduced echelon form, but the rank of the matrix of S. Right, so where's my green color? So that's going to be the rank of the matrix A associated to each of the columns mentioned in S. All right, so what is the span of this? So the span of S is going to be the 2D set. So it's going to be a 2-dimensional plane containing 3, 2, 1, and negative 1, 2. So it's not of R3. So let's just do a quick geometrical understanding of this, right? So let's assume that this is my XYZ plane, right? So let's assume that 1, 2, 3 is located somewhere up there, and negative 1, 1, 2 is located somewhere there. Let's actually connect these points with a plane, right? So for example, that would be there. Let's actually do this in the same exact color. So let's do this here and that there. So if we were to make a plane out of those things, then you're going to have sort of this plane hanging out in R3. So for example, if I were to pick this point sort of way back there in the distance, which is not going to be on that plane, and that's not going to be on there. But any vector on side of this plane, for example, if I were to connect the origin to that particular point, that would belong to the span of that vector. So that would be the span of those particular vectors, just some two-dimensional subspace of R3. Let's look at another, probably easier to understand example. So example 3. So let's consider the set S is equal to 1, 0, 0, and 0, 1, 0. So obviously these two vectors are going to be independent. Both of them belong to R3. So what is going to be the span of that set? So notice that I can get any vector along the x-axis and along the y-axis. So one can say that the span of S is a two-dimensional subspace of R3, but in particular it's the xy plane. Right? So if we were to sort of graph this, right? So let's assume that's x and y. So 1, 0, 0, that's going to be that vector there. 0, 1, 0 is going to be there. So any vector in the xy plane you should be able to get, but you will not be able to get anything in the vertical direction. You'll only be able to get things in the horizontal direction. So just anything in that surface you will be able to get in the linear combination. So any vector, for example, there would be fair game. But if you had a vector sort of, flying out into the sky or below the ground, that would not be along to the span of these two vectors. Let's just do one more example of a span of vectors in R3 just to see if we get the big picture. So let's assume we have S is equal to 1, 3, 2, 2, 3, minus 1, minus 2, minus 6, minus 4, 4, 6, minus 2. Just take a look at these vectors and see what you can gather just from observational purposes. You should be able to see that these two vectors are dependent on each other. One is just a combination of the other, and these two vectors are linear combinations of each other. So one could say that the span of S is a linear combination of U1, U2, U3, and U4, but they are a set of dependent vectors. One depends on 3 and 2 depends on 4. So the span of the set of vectors, although it is a linear combination of U1, 2, 3, and 4, technically you can just write it as the span of the vectors U1 and U3, or you could also say that the span is equal to the same exact span, for example, of U3 and U4. As long as you're choosing pairwise independent vectors, then that probably is the best way to represent a span, right? Because again, 1 is dependent on 2 and 3. 1 is dependent on 3 and 2 is dependent on 4. So for example, 1, 2 is okay, 1, 4 is okay. You could do 3, 2, or you could do 3, 4. Any of those combinations would be perfectly valid when you're talking about the two-dimensional subspace of R3 for which these 4 vectors do span. Throughout the last couple examples, you may be able to pick up on some important characteristics about spans of vectors in sets of vectors Rm. Let's just look at the general case for R3, and let's look at a few cases for which you may encounter. So let's choose 4 vectors, all of them belonging to R3. So we have 4 R3 vectors. So we know that if we place all of those columns in some matrix A and do the reduce for echelon form, we could get a variety of different scenarios. For example, if we look at scenario 1, notice that columns vectors 2, 3, and 4 all depend on column 1. Therefore, there's only one independent vector there. Therefore, there's 3 dependent vectors in that set. So it's a set of dependent vectors. In scenario 2, notice that we have 2 pivots. So what does that exactly mean? So that would mean that the other 2 vectors are dependent on those. In particular, vector 3 depends on vector 1, and vector 4 depends on vector 2. We can see that from the reducer echelon form, which is pretty nice. If we look at scenario 3, again, we have 2 pivots, so who is dependent on who? So vector 3 is dependent on vector 1 and vector 2, but vector 4 is only dependent on vector 1. Again, it's a dependent set of vectors. These other two cases probably are the most ideal scenarios that you can have, because remember that the maximum number of pivots that you can have in a matrix is equal to the number of rows, which is the dimension of the space of vectors that we're working with. So these are two of the scenarios here, right? So notice that vector 3 in this first case is dependent on vector 2. And in this last case, notice that vector 4 is dependent on vectors 1 and vectors 3. So these two sets of vectors are, of course, dependent sets. Actually, all of them are sets of dependent vectors, right? But notice that even in the most ideal case for the maximum possible rank, remember the maximum possible rank of a particular matrix A is equal to the number of rows in A, which in this case is going to be equal to M, which for this particular example is going to be equal to 3. So, what theorem can you generate about a set of vectors that has more vectors than the dimension associated to the space for which they come from? So let's formally state it here, and I'll leave the proof for you. So let us assume S is a subset of vectors of Rm, and let's say this. If the size of S, and let's suppose that there's n vectors, is greater than m, then S will always be a set, of dependent vectors. Always. So let's just illustrate that with an example. Suppose I have S is equal to x1, x2, x3, x4, x5, and let's assume that all of these come from the vector space R4. Notice that I have 5 vectors. In the most ideal case, since I'm sampling from R4, the maximum number of rows in each of these vectors is going to be 4. So we can take without loss of generality, for example, that the first 4 vectors are the independent from each other. That means vector 5 must be dependent on at least one of the other 2 vectors, and therefore that is a dependent set. Right? And also another interesting thing that you may want to think about, question, what if the 0 vector belongs in that set S? Will that always be a dependent set? Will it sometimes be a independent set? While you think about that, keep in mind today we just talked about linear combinations, spans of vectors, and sets of dependent and independent vectors from the perspective of linear combinations, and how we can assess a set of vectors as being dependent or independent via the reduced for echelon representation. So I hope you enjoy, and I'll see you in the next video. Take care.